Okay, so first I would like to start with what to expect from this workshop. And this is a workshop actually for you to give some basic idea or some basics of the machine learning and deep learning, so that later you can maybe consider starting applying some of these methods for your own research. And here you see the GitHub account that includes all the material that I'm going to cover today. I mean, I may not be able to cover all of them, but I'll try to do my best. So basically, this material contains two major parts. In the first part, I will cover some machine learning basics. I will first give some idea about reading and visualizing data and give some play examples on supervised learning that includes classification and regression. Then I will do some example on a real world problem. And if the time allows, I will try to give some background and the fundamentals of the deep learning approaches. And one of the well-known deep learning libraries called TensorFlow. And here also we will cover some basics and with some application. So this material will stay here in this link, and you can also download the material after this workshop. Basically, in order to run this material, first you should download, you should open your basically terminal or command window in your computer and type this command so that you can download all these material into your local computer. Then I put some data, some large data sets that we are going to use in this workshop to this link. You can also download this data from this link and basically copy into this folder. There are a couple of ways of running these materials. One can use their own computer, but this will require some further installations. And I will give the installations instruction in this TXT file. Other option is to use a cloud platform called Google Cloud. In Google Cloud, you can basically upload all the material in your Google Drive folder, like this, file folder name like ML Workshop, and then you will see all the material here. Let me start with the machine learning one. And the notebooks or the coding material that we are going to cover are named with this IPython extension. So these are the files that you are going to run by your during the workshop, and if you want to run them by yourself after the workshop. And some of these materials are left as a practice for you to complete later, and the solutions can be found here in the solution folder. So, okay, to open these IPython notebooks, first right-click on the folder and click on this Google Collaboratory. So especially in the deep learning part, you may need some GPU power because training neural networks on CPUs takes lots of time. So Google Collaboratory allows you to use GPU for free for a limited time of 12 hours, I think. So in that sense, you can run all the codes without requiring extra hardware, and you can use your own computer. Okay, in this first notebook, the first talk that we are going to cover is reading data and doing some simple visualizations. So the platform that we are using is called Jupyter Notebook, and Jupyter Notebook, as I said, allows to run these IPython files, and we are going to use Python during this workshop. So first, so the code are divided into different cells like this. In order to run a code in a particular cell, you can basically click on this play button or press Control plus Enter, as you see here, or maybe Shift plus Enter. So I'm running this to include some libraries. So this should finish to make sure it is like included. Now we included all the libraries that we are going to need. So these are actually 3 common libraries that you can use in your work as well. Numpy is a very well-known numerical library that allows you to perform matrix or vector operations in an efficient way. And it contains many functions that allows you to easily do some operations such as matrix multiplication, taking a mean of a vector, maximum of a vector, etc. Matplotlib is another library that we frequently use in machine learning for data visualization. Basically, you can plot your data and see how data looks like, so that you can maybe get some idea what kind of model to fit your data and like the what machine learning algorithm to choose. And Pandas is the last library. It is designed like for data handling, which is similar to R. So as I said, we moved all of our folders to Google Drive. And in order to be able to reach those files through Google Colab, we first have to mount our Google Drive into this Colab environment. So for this, I need to run this cell, and this will ask for authorization. I should click on this link and basically allow Collaboratory. Sorry, I should hide this video panel. Okay. And copy this key here. And we're waiting this to finish. Okay, now we mounted our Google Drive to the Collaboratory. So next we go to the directory that we're going to work on. And let's check if we are in the correct directory. Basically, we see all the folder and file names that we see here in the main folder. Okay, so first, we are going to give some examples for regression and classification. Let me quickly try to introduce the regression problem. In regression, the goal is to approximate a mapping function from an input to an output. And here, the output can be either an integer value or some continuous floating point value. And to give some examples for the regression tasks, for example, if you want to map the salary of the person to the rent of their apartment, this is a regression problem because the rent can take many different values. Or if you want to map a person's brain MRI image to their age, this is also can be considered as a regression problem because the age can take various integer values in this case. So let's start by reading some data. We have some data sets in this material. Let me go to the directory here. Under this data folder, there are many TXT and CSV files here. So we are going to first read the features that we are going to use for prediction. So here, let me first give what are the features and what does feature means and what does label means. For inputs, we also sometimes refer them as features. And for the outputs, we also call them as labels. So to read TXT files, we use Numpy functions called load TXT. And here we write this as NP because we defined Numpy as NP. So if we change this definition to anything, here we can write anything we want, but NP is a convention. We have to use the same naming here. And load.txt is a Numpy function. So we reach this Numpy function by putting a dot in between. So we give the path where our files are located. By doing this, we read features and labels. Let me run this. So in the meantime, maybe I can open the files as well. This is feature, and this is for the labels. So basically, these files are structured like this. Each row here corresponds to a different data point. And basically, we have only a single feature here. And in the label part, we also have like continuous values that we are going to predict or use for the prediction. So basically, this first line here is the ground truth value or the label value for the first feature here. So let's, for example, print the data that we read. If we run this again, we will see the features as a very large vector. So if we check these correspondences like 8.6, 14.2, and so on, and this is aligned with this order. And same holds for the labels as well. And in total, we have like 100 data in our data set. So Numpy also allows accessing some parts or some slices of the features or arrays. This means that accessing first 10 elements of the features. And I can, for example, also write this. This means that let's print the features between the third element and the 10th element. And the second index is not included. And if you want to access to a single element, you basically write this. And in Python, indexing is starting from 0. Okay, so we read our data set. Now let's try to visualize it to understand how it looks like. So PLT, as I mentioned, is a matplotlib library, which we imported here. We imported as PLT. And scatter function of this PLT performs scatter plots, basically. So this performs 2D plots, and we give features for the values in the x-axis and the labels for the values in the y-axis. This grid on puts these grids in the background, and these labels basically put the features to the x-axis and y-axis. You can play with the code by commenting some part. So this hash, putting hash here means that this line of the code is not considered, it is commented. So it is not evaluated by the compiler. So for example, if we comment this part, so we will not see the label for the y-axis basically. Okay. So let's also load a data set for binary classification. Actually, in classification, our goal is again approximate a mapping from an input and output. But here, our outputs are discrete variables. This is the basic one fundamental difference between classification and regression. So to give some examples to this, for example, we have like a text of an email as input, and we want to classify them whether this email is spam or not, or we have like a person's MR image as input, and we want to classify them whether this person has a brain tumor or not, or like we have an input as a like person's lung CT image as an input, and we want to label that person whether this person is COVID positive or not. So similar naming convention holds for classification as well. So we call the inputs as features and call the outputs as labels. And for classification, you can also find some resources that calls the outputs as categories. Let me close these guys. Okay, in the classification examples, now we are going to read data from CSV files. So those CSV files are also located under this data directory. So let me find it. Features near classification, features near classification.csv. Okay, so we can open them as Google Sheet, and we have another file for the labels. So as you see here, we have two features, whereas in the regression example we had one feature. We could also have like regression problem with multiple features as well. So these are just examples. And here we have, again, 100 data points. And each features are labeled like feature 1 and feature 2. And in the label CSV file, we have labels for each data point. So the first 50 data points are labeled as 0, and the rest are labeled as 1. So this is basically two-class classification, which means a binary classification problem. So let me run this cell as well. Okay, to read from CSV files, we use Panda library, which I again imported in the beginning as PD. And PD.readCSV function is used to read CSV files. And similar to the load.txt function in Numpy, we give the path here and it returns the data in the CSV file as output. So we read features and labels here. And we can get the dimension of our data by using the shape function, because this is a NumPy array, and it has a function called shape to return the function. Actually, this shape function, if we omit the 0 here, it will return a pair, like 100 by 1. And if we reach to the 0th index in the pair, we will get the number of samples. And if we reach to the first index in this shape, we will get to the number of dimensions, which are 100 and 2 respectively. Okay, I think that's all I want to say here. Okay, now we read the data and let's try to visualize. So this is basically binary classification problem, and each data point has a label, as I mentioned. So let's visualize the data from the positive class by plus and from negative class, or the data with class label 0 actually with minus. So here, let me print this post rows, and to see what this greater operation does. So basically, this function or this notation here returns either a true or false, depending on these conditions. For the values inside the label satisfying these conditions, it will return a true. And for the ones that doesn't satisfy these conditions, it will return false. So basically, in these indexes, we will have true for the samples from positive class and false for the ones from the negative class. And here we do the opposite. We get the true output for the negative class and the false output for the positive class. So basically, this allows us to extract the indexes of the class of the data samples based on the label values. So here we plot the features of the positive class samples, and here we plot the features of the negative class samples. So x in x axis corresponds to feature 1 and y-axis corresponds to feature 2. And this grid-on thing is similar as we do before, and this is the labeling part. So here also we see our data. So far we solved 2 problems for regression and classification, and we could visualize the data. So why do we use visualization? Actually, this is mostly helpful for low dimensional data, because for the higher dimensional data, it is more difficult to visualize data points in such a nicer way. But if you have a lower dimensional data, or if you have a way to reduce the dimension of your data, visualization of your data allows you to get some idea about the distribution of your data, and accordingly you can choose an appropriate model that represents your data. For example, for this regression example, if you want to fit a model for this regression example, I think one of the best choices would be a linear line aligned like this, because this will be probably the one of the best linear model that represents the data. And in the classification case, so we want to find a decision boundary that distinguishes positive and negative classes. So probably a boundary around here would work for this data set. So for example, if you see such a distribution when you plot your data, then you can decide that, okay, a linear model can work like to some extent for this data, or a linear model can represent my data and can be useful for my problem. You can make a conclusion like this. So last, I'm going to show you how one can read images. Reading images can be slightly different than reading other types of data. Here, I will give some particular example used for medical images. Nibabble is a library that is quite useful for reading medical images. So here we have an example nifty image, and I use Nibabble's load function to load this image. And when I print this I, basically it will print all the metadata information inside the nifty. So with getFdata function, we can convert nifty images to Numpy array. So that, because in Numpy it is easy to process data, and most of the built-in libraries in Python are developed for Numpy, so it is easy to process such data. So by v.shape, we can get the dimensions of our image. So this is basically a 3D data, and that can store flow64 values. And if you print type of this data, you can see that I is a nifty image and V is a Numpy image. So, which means that the conversion is successful. So let's try to visualize this 3D data. So visualization in 3D is you know, not quite easy. So we can visualize some slices along different directions, like to understand how our data looks like. So we extract the middle central slices in each direction, and here we use plot imshow, and we give this slice as a input for the secondary plane, and cy as input for the coronal plane, and cx for the input for the axial plane. And cmap gray allows you to visualize this grayscale image, not like a heat map. So at the end of this section, there are some exercises which I'll let for you to complete after this workshop maybe. And there are like instructions are written here, and you can basically consult the code above to complete this part. So I think this is all for the first part. And if you have any question about this reading data and visualization part, maybe I can take some questions, or should we wait until then? I don't know.
No, I think it's perfect. We can make the break and ask questions.
Continue with the next part.
Thank you.
Oh, okay. So in the first part, we like load and visualize the data, and let's now try to fit some simple machine learning models to data, and specifically we will use linear regression for regression problems and logistic regression for binary classification problems. And as we did before, we have to import the necessary libraries, and we need to mount our Google Drive. So let's go to the main directory and check if we are in the correct directory again. So this part is something that we already did to visualize the data. And we said that a linear model could be a good fit to represent this data in our model. So, so we will see a linear model, how to fit a linear model in Python. So scikit-learn is a library, is a machine learning library that contains like implementation of many different machine learning algorithms. So to import this from sklearn module, we need to import linear models to reach the different linear models to fit your data. So once we import this, there are, as I said, many different algorithms that are implemented. And one of them is linear regression. So first, from the linear model library, we call the linear model class. So basically, here we create a linear regression object. And here, we only created the object. So we haven't started like fitting some model to our data. For fitting, we have to call the fit function of this reg R object, and we have to give the training data for as input. So basically, we have to provide this fit function to our features and the corresponding labels, so that the linear regression can learn from our data. So this works quite fast. So here the optimization is done, and we learn the parameters of the model that fit to our data. So let me briefly talk about what happened in the background. So basically, linear regression solves this optimization problem. So here, X n's are our features, and we have n data points, and Y is the corresponding labels. So basically, Yn is the ground truth. And since we have a single dimensional input, we have such a linear model. So this is our input, and Xn plus B is the prediction of our model. So ground truth minus predictions is squared here, and it is summed over, which means that we are trying to minimize the distance between the ground truths and our predictions. And we do this minimization with respect to the parameters, with respect to the model parameters, which are A and B here. And after minimization during minimization, we find parameters A and B such that this equation is minimized over like all these n training samples. So here we fit a model, and let's see how good it fits to our data points. So we also use it, we also visualize it by plt.plot. So basically this part plots this blue dots as we do in the previous example. So, and we have a starting point here and an end point around 30 and starting point around 0. So by giving 0 and 30 to our model, we can do predictions for these particular points. So when we give 0 as input to our predict function, this will predict something around 5. And when we give 30 to our predict function, this will predict something around probably 1.8 or something. And we will plot a line between these data points. And this red line represents the model that we fit to our model. As you see, it is like not a very bad representation of the data, because most of the data lies in this linear line. So after fitting this model, we basically use this predict function to make a prediction on our test data. So one thing I should note here is that, so all the blue points here are used during training, but our model makes some error even in the training data as well. For example, the prediction for this blue dot here is above 4.5. Sorry, the ground truth value for this blue dot here is above 4.5, but our prediction is around 3.5. So there is even some error on the training data. But for some of the data points, the predictions are almost like quite perfect. But in order to evaluate the real performance of a machine learning model, we have to see its performance on real test data. For this, we first read our test data from this txt file using mp.plot.txt, as I introduced in the previous notebook, and use this predict function to make predictions on the test features, and these are our predictions. Let's visualize this. As you see, all of our predictions lies on this line, but this doesn't yet give us much information, any information about how well are our predictions. So for this, we need to get the ground truths as well. First, we need to read the labels and plot them onto in the same figure. So basically the black dots here are the ground truths. So you see there are still some errors. For example, here there is almost no error, but our model, I mean, our very simple linear model makes quite like a good representation of the data set. So let's try to quantify this error. So total test error basically is the squared distance, sum of squared distance between the labels and our predictions. And if we take the mean, this will give us the mean squared error. And if we take the square root of this, it will give us the root mean squared error. So these are the common metrics to evaluate the performance of a machine learning model in regression. And these numbers will help you to quantify the error. Okay, so here's also another exercise for you to complete for the regression part. And let's switch to the logistic regression part. Logistic regression is has also a very simple model. We have a linear model, which is passed through a function denoted by sigma here. And here X represents our features and Y represents our labels or predictions. And here sigma is the sigmoid function. And the good thing with the sigmoid function is that this function squeezes any value given here into the range 0 and 1. So therefore, there's a probabilistic interpretation of this model. So the output values can be considered as probabilities. So yeah, this X doesn't have to be a single feature. We can also write multiple features here, and still we can build a linear model. For this example, we will use the example in the previous notebook. You plot the data. And as I mentioned, a linear model can do a good or reasonable job when separating these two classes. We imported the linear model from the sklearn library. Remember this import here. And this library also contains a function, class for the logistic regression. So we create an object and fit a model. So as you see, actually nothing has changed compared to the linear regression except this function here. Actually, in terms of the notation, there's nothing much change, but in terms of the optimization, there are some changes. So basically, logistic regression optimizes this loss, which is like the cross entropy loss. Basically, AMs matching the distributions of correct labels to the predicted labels. I'll not go into the much details of cross entropy. And let's predict our data. So, okay, if you forget to run this cell. Okay, if you don't run this cell, you see some error because class wasn't defined. So this time should probably work well. Okay, so here we plotted the decision boundary. So in this first part, we plot our data points. And in the second part, we plotted this red decision boundary based on our predictions. As you see, although there are some mistakes, even in the training data, it looks like the separation is like quite good for the training data we have. So let's also see the performance on a test data. We read the data, test data for classification from a TXT file using Numpy load.txt. And again, we use the predict function to make a prediction. And this predict function was same also for the linear regression case as well. So there is nothing really changed in terms of using the sklearn library, which makes like running such models or using such libraries very convenient. And as you see here, you can see the predictions. And let's visualize the labels. And here, the green ones indicate the correct predictions, and the red ones indicate the wrong predictions. There are cases, of course, that the model makes wrong predictions because it was already doing some worse predictions, bad predictions for the training data as well. It happens on test data as well, but this is like reasonably good because this is much less compared to the wrong predictions. So let's quantify this. So we measure the classification accuracy by checking by checking the computing the number of data points that we correctly predicting. And we also measure the false positive and false negatives predictions. And false positives are the one that we predict as positive class, but the label is negative. And the false negative is the examples that we predict as a negative class while their label was, were positive. And after this evaluation, we see that our classifiers, the total accuracy, prediction accuracy of our classifier is around 95% with the false positive rate 0.05 and false negative rate is 0.1. Yes, I think that's all in this notebook as well. So if you have any questions, maybe I can take those and continue later. So in the previous notebook, we basically fit some linear models, linear regression and logistic regression from the sklearn library. But there are many different algorithms implemented in sklearn, and we can use those also for our application as well. So let's mark this. Yes, in this notebook, we will explore these additional algorithms that are implemented. So here, there are some helper functions that we are going to use for visualization. So basically, they use matplotlib plot functions. So I will not go into detail. And let's visualize our data again. And we did this step in the previous notebook actually, which was like using logistic regression for classification. And this is the decision boundary that we get after optimization. There is also another method called support vector machines that is frequently used when fitting models to your data. And here, to use SVM, we import SVM class from the sklearn and basically define an SVM object and call the fit function. So again, the only thing that changes is this import and the way you define your object for a particular method. So SVM has a parameter called kernel. If you put here like a linear kernel. If you choose a linear kernel, you will end up with a linear model. So you can also use more complex models with SVM as well. Like one option is the polynomial SVM. And you can basically try this by changing this keyword here. Another algorithm is a decision trees. And you import tree, and from the tree library, you call the decision tree classifier class and define an object. And similar to the previous methods, you call the fit function to learn the model. So here you see that the fitting to the data or the training data is a bit better compared to other methods. But it is hard to say that for now at least, or without the validation or holdout set, which model is better than the other for a particular example. Because here there is not much error on the training data, but this division is not quite intuitive because this model will classify any data point, any test data that lies somewhere here as negative class, while like most of the positive classes are like gathered in this part of the region. So we are very likely to make a mistake around these regions. So this is like can cause a overfitting problem, or this model overfits to our training data. And random decision forests are another algorithm that is ensembling based, that ensembles multiple classifiers and reach to like a final classifier. Here also we see that the fitting to training data is quite nice, but we cannot argue that this is the best fitting that we expect, or it's the best model that we need to choose because of the overfitting. For example, here all the labels here will be classified as negative, but it's very likely that we can end up with having a positive example here. And also you can try neural networks with the scikit-learn library, Basically, you can write a scikit-learn.neural network and import multi-layer perceptron. Here we have two hidden layers in our model, and we are fitting a model here. So this is also, since this is a multi-layer neural network, this also finds a nonlinear model. And we can increase the number of hidden layers in neural networks. And as we increase the number of hidden layers in the neural networks, we can build more complex models. But more complex model does not mean that the fitted model is best for us due to overfitting. So here you also see that this model overfits to our training data, and it is very likely that it will make wrong predictions for the test data points that lies here. So in practical, actually, the simpler models are less likely to overfit the training data, although they are like more likely to as they are more likely to generalize to unseen test data. So the general rule of thumb here is that to choose the simplest model that provides satisfactory performance. And how to measure this performance? Cross-validation is one way of doing this. Basically, in cross-validation, you split your data into k-folds, which is called as k-fold cross-validation. And in each time, you use the k-1 partitions for training and use the rest partition for validation or measuring the model's performance. And you do this for every split. And basically, you will train your model k times at the end. And you will report average accuracy to report the real, like a generalization performance of your model. This is a better metric because in most applications, our training data is like small, and we might be really overfitting to our training data, and this may not reflect the real performance of our model on the test data. So let's read some features and labels and visualize it. And let's train two models. One is the logistic regression and another is the multi-layer perceptron classifier. For the k-fold cross-validation, it is actually very easy in sklearn library. It is imported inside this model selection module, and you can import it as certified k-fold. And when we import this, we create a certified k-fold object, and we define the number of splits here. This is the k value that I mentioned in the above definition. So basically, this loop, or when we call this skf.split function, this will produce different folds from our training data. And let's print the training and testing indices in each fold. As you see, they are not overlapping each other. And each time we have different test indices. So this library does this job for us, and it is quite easy to use in our application. So let's measure the performance of this logistic regression and neural network models and compare them. So again, we created the certified k-fold object. We initialized vectors that stores the accuracies for each fold. This is for the logistic regression model, and this is for the neural network model. And here we create the splits. In each run of this for loop, we will run the model on different training and test splits. Here we fit to the training data for that particular partition. And we make the predictions for the rest of the partition that we use as test. And here we compute the accuracy, prediction accuracy. And this accuracy score is a part of this library. And after completing this loop, we will have accuracies for each fold, and we can report the accuracies here. So these are the accuracies for each fold. You see there are some high numbers here, mostly very high numbers, and the generalization accuracies. As you see, the simpler model, logistic regression, generalizes better compared to a more complicated model, neural network. So yes, I think this is also all for this notebook. And if you have any question about this part, please feel, yeah. So here, I think maybe this can be the last notebook that we can cover today. We will do some example on a real world data set. Yeah, I will come to data set later. Let's do these import and mounting things. Okay. So here we will, so for the low dimensional data that I showed you in the previous notebooks, things were much easier because a linear model was able to represent our data quite well, and we were able to visualize it. In imaging data, we often end up with high dimensional features. And it is difficult to visualize these features in a high dimensional case, and it is difficult to find out which model is perfect for our case. So here we will do an example for Alzheimer's disease classification. The first example is to classify subjects with Alzheimer's disease as healthy or non-healthy, using the cortical thickness maps. We will use cortical thickness values extracted from 290 individuals. So let's read the features and the labels first. So here you see the number of subjects, number of features, and there are like an equal number of cases from per people with Alzheimer's disease and healthy. So in this example, we will use a linear support vector machine model. Okay, and we will we will perform k-fold cross-validation. So since we have like a larger data set here, this takes a bit longer. So this is the accuracies that we get in each fold, as in the previous example, and this is the generalization accuracy estimate of the model. And in the second task, we will perform age regression using volume of different anatomical structures. The underlying idea here is that the age, as human age changes happen in the brain, so we will try to predict age from anatomical structures of the brain. So let's also read the data. So here we have 335 subjects with 45 features. And here, this is the mean age in the data sets with the minimum and maximum values. We can always use Numpy functions when computing these values of mean, max, etc. And this is a regression model, and we will use a lasso model this time, which is like a different than the ones that I used before. So this model also included in the sklearn library, in the linear model library, and its usage is like quite similar to the previous ones. And we will, at the end, we will report the mean squared error. Here also we compute the k-fold. We allocate the arrays for accuracy in each fold or error in each fold. And in this loop, we fit a model and we fit a model for a particular split, training split, and test on the remaining one. And at the end, we measure the error, basically. So here are the accuracy estimates, accuracies for different folds in terms of RMSE and in terms of Pearson correlations. And this is the average of them, which we can report as the generalization accuracy estimates. Okay, this was also an example related to regression and classification. And this is also end of this notebook. So I think we can finish this here and take the questions instead of like going into the deep learning part, because it will require, I think, more time, which we cannot cover in like 15 minutes. What do you think?
That's perfect. Thanks a lot. Maybe I can also remind you that in case you want